talk, you realize that the speaker is somewhat old. Wait a minute, I've got to get rid of that thing from my screen. That's the first problem we've got. There it goes. Okay, so yes, when the introduction to the talk takes at least almost as long as the talk, as I say, you can conclude that the speaker is getting kind of old. In fact, I've been a professional mathematician since getting my PhD for about 50 years now. And the first 25 years, I just did pure mathematics, working on solving abstract problems, producing papers, going to conferences. Didn't care where the mathematics came from, didn't care how it was used. I just did mathematics because I loved it and I enjoyed it. And I still love it and enjoy it just as an intellectual discipline, as a game I play. To me, mathematics was like rock climbing, long distance running and cycle racing. They were just problems and challenges that I used to like to try to meet new challenges. So that's how I regarded mathematics for the first half of my career. In the second half, I began to get much more interested in the way mathematics was used in society. While I was still living in the United Kingdom, I started working on some problems related to language and communication. That interest took me to Stanford, because Stanford is one of these places where it's not only extremely good research in mathematics, but also a lot of people take mathematics and use it in all sorts of ways. You know, it's sitting in the heart of Silicon Valley. And once I got to Stanford, my interest in applications just blossomed, and I ended up working on all sorts of projects, construction projects for the European community. After September 11th in the United States, I was working for the intelligence services in the US to try to improve intelligence services. Then I worked for that was actually the NSA. Then I worked for the US Navy, then for the US Army and various other places, using mathematics to do things to help people in societies. Initially to try and stop terrorist attacks, but then to do all sorts of other things. And in doing that, excuse me, I developed a very different perspective of mathematics, one that still encompassed pure mathematics as its own discipline, which is how we usually think of it, but also mathematics as a part of human society, as a way of thinking that humans have developed over 10,000 years to understand the world we live in, to describe it with greater precision than you can if you don't have mathematics, and then to do things in the world, to become engineers, to become scientists, to develop societal structures. All of that came about as human societies developed, and the development and use of mathematics has been a part of and a driving force for increasing structure in society. And now I seem to have lost my ability to advance this. Wait a minute, something has held up at this end. There we go. So what I want to do now is, I'm going to begin by providing you with a picture, a simple picture to sort of understand how mathematics sits in society. And the idea is this: as people, throughout history and in the world today, human beings encounter situations. We're in situations, we develop situations. So we are people, we're in some part of the world, and we have a real world situation. We can do all sorts of things in there. One of the things we can do is we can develop and use mathematics as a way of thinking about that situation. And the way this works is we take that real world situation. I'll give an example in a moment. I'll give two examples, in fact. We take that real world situation, we abstract it somewhat, and we express it in some technical language. That gives us a technical description. We can then take that technical description. Now, by the way, the technical description, it could be in the language of physics, engineering, finance, commerce, sociology, education, the different worlds, medicine, all of the different ways that we have of thinking, different areas of expertise. Each area of human expertise develops its own technical descriptions, its own language. So we can take a real world situation, we can then express it in a technical terms as a technical description. And then if we want to use mathematics, we can take that a step further, and we can abstract from that technical description into the language of mathematics and get a mathematical description. So now we've sort of gone away from the world. We've had two levels of abstraction. The classic example of this is with physics. Physics itself uses mathematics explicitly. So in the real world, you take the world, you think of it in terms of things like forces, accelerations, all of this sort of the language of physics, mass, temperature, and so forth. Those are all the terms from physics. Then you can take those terms from physics and you can express that in mathematics. And indeed, physics itself does that. It develops itself by developing the mathematics of physics. Once you've got it in mathematical language, formulas and equations and so forth, you can then do the mathematics. You can start solving those equations. You can start developing those spreadsheets, doing the calculations. You can do all of that stuff to get results. And then those results, you can feed them back into the world and do things in the world or to understand the world in a better way. So by following this cycle round, and it's what I call the mathematics cycle, you can think about the world in a way that allows you at one point, at the top right-hand corner of that triangle, at that point, you can be very precise. You've lost a lot. Once you describe the world in terms of equations and formulas, you've lost a lot of the world. In fact, you've lost most people because very few people can understand that. But you've got a description which has traded complexity and depth and breadth for precision. So that's the trade-off. You get precision. If you go to the level of mathematics, you get total precision by abstracting, by forgetting a lot of stuff. And the two examples I'm going to give right now will illustrate what I mean by following this cycle round. The first one is actually one from fiction. In the period 2005 to 2010, I was one of the advisors on a very successful television crime series called Numbers. And the idea of Numbers, excuse me, in the top left-hand corner, we have two characters. The one in the front is an FBI agent, and he has a younger brother. So the FBI agent is called Don. He has a younger brother called Charlie, who's behind him. And Charlie is a mathematician at a fictionalized Caltech University. Couple of interesting things about this series. It was based on real use of mathematics in criminal investigations. And it was set on the campus of Caltech, where all sorts of work is done that way. In fact, the main advisor on the series was the head of mathematics at Caltech, who actually does lots of work with the legal system and with law enforcement. And he and I and a bunch of other mathematicians were advisors on that series. And in fact, it was when I was working on this series that I developed this picture of the mathematics cycle, realizing that it's what I'd used and mathematicians had used all our careers, and it's the way mathematics has always been used throughout society. This going from real world to a technical to mathematical and mathematical results. This is the picture for mathematics use and the development of new mathematics, and it applies to the entire history of mathematics. And as I say, I developed this picture by working on a TV series because this was a crime series. It was a popular series. In fact, it was one of the most popular series of all time. It used to get audience of about 15 million people every Sunday evening. So, and that's why it ran for 6 years. A typical episode, in fact, every episode had the following format. It begins with a crime, and you see a depiction of a crime, okay, or the discovery of a crime. The FBI is called in, and Don and his colleague go in to look at the crime, and they interview witnesses, they measure things, they take that complex crime scene and they describe it in the language of law enforcement, using all of the techniques they have with interviews, collecting data and so forth. And then at some point in the investigation, Don finds out he can't go any further because he seems to need some mathematics. So he turns to his brother. By the way, this whole thing was developed precisely to portray mathematics as it's actually used. The two co-creators that I got to know very well, their whole goal was to try to explain to people through fiction how mathematics is used. And it is, as I say, working with them that's helped me crystallize this picture to visualize in a simple diagram how mathematics gets used. The content of that diagram is familiar to all mathematicians. There's nothing new to mathematicians, but it is new to non-mathematicians because non-mathematicians typically think mathematics is what happens in the school math classroom, which is not. What you learn in the school math classroom is the basic details of how to do mathematics and think about the world using mathematics. You don't actually do that except maybe for a few examples. So going back to the series, Charlie then comes along and does some mathematics. You see him talking to his brother. That's the handover between the language of crime detection, the FBI's language, and the language of mathematics. You literally see that as the two of them brothers talk about it. And in this particular images are taken from the very first episode. And that equation is shown on the screen in the first episode as the mathematics Charlie comes up with. Once he's formulated that equation, he actually works with that. He develops a computer visualization to try and understand what's going on with that equation. And he gets results. And in this case, the results, and this is about detecting a crime, what the FBI agent, what Don wanted to do, was find where the perpetrator of that crime lives, because they want to go and find him and arrest him. But they don't know where he lives. The whole thing was set in Los Angeles. It's a big city. But Charlie, doing the mathematics, comes up with a contour map which shows the likely probability of where that person lives. That equation has things called PIJs. Those are probabilities based with grid entries on a map. And so that tells you the probability of where this person might live based on the crimes that he's been committing. So Charlie then develops that map and says, if you look at the center of that map, what he calls the hot zone, the little yellow area in that map, there's a very high probability that the perpetrator lives there. And that's about 100 houses. So at that point, the FBI can come in and start using observations and just going around the neighborhood, trying to track that person down. And then the feedback is they actually go and send in the FBI agent and arrest this person. Okay. In this case, many of the early episodes were based on real cases. Eventually, they ran out of real cases to keep a lot of series, but they kept inventing cases that could have been real. But the first one actually really was real. It was based on work by this person, Kim Rossmore, who was a Canadian policeman in Vancouver, who left the police force to go and do a PhD in sociology. And he looked at the sociology of serial criminals, because serial criminals are sort of pathological creatures who tend to have very mathematical, methodical behavior. And you can track it using the language of sociology. And in Rossmore's case, he was also a math fan. So not only did he learn the sociology of criminal behavior, he was able to turn it into mathematics. And that was the equation he developed in real life to find where serial criminals live. And he founded a company called Criminal Geographic Profiling, Inc., that hires itself out to police forces. The technical descriptions then were this one person, he took the language from the FBI, well, he knew language from police because he was a policeman. He turned that into the language of sociology to study the behavior of people that behave in very predictable ways. Well, we all behave in predictable ways, but pathological serial criminals are particularly mathematical in their behavior. And in that case, he was able to come up with a formula based on just linear algebra. And then Charlie in the episode does the math. By the way, what Rossmore did was he actually did start producing these maps and doing things like that. And in fact, when you see Charlie do it on the screen, they're really just taking the history of what really happened in that first episode. So that's the way it worked in real life. If you're interested in this, I wrote a book together with the math professor at Caltech, who was the main advisor on that series, Gary Loden. He and I wrote a book based on the first two seasons where we look at the real mathematics between some of the episodes, including that one I just mentioned. And as I say, in the first 2 seasons, all of the episodes were either based closely on real cases or based loosely on real cases, or they were fictionalized cases that could well have been real cases. So the mathematics is all genuine. And we describe that mathematics in that book. It's a great example of mathematics because people are surprised that you can use mathematics to catch criminals. But the FBI have been doing that for years, and the NSA and the CIA and the various intelligence services use it to track terrorists and prevent terrorist attacks. Okay. So that's the general picture. As I say, I developed this image by working on that series and thinking of it as a plot, because that diagram is the plot line for every single episode. That is the dramatic plot line of every episode. And it's so clear in the series in a way that's much more clear than in real life with its complexity. Okay. That part on the right, where once you have the mathematical description, you do the mathematics and you get the results. That's the kind of activity I spent the first half of my career doing. That's solving equations. It's working on mathematics. You don't need to know about the real world situation. You don't need to know about the technical description in some person's expertise language. And you're not interested in the feedback. If you're a mathematician, a pure mathematician, you work inside that box. You're working with a model, you're interested in the model, and if you like that stuff, it's wonderful. And you don't need all of the outside feedback. However, as I said, in the second half of my career, I got very interested in the way that mathematical model or those mathematical models fit in society, because this is a technology. Mathematics is literally a technological tool that humans have developed, a cognitive tool that we've developed to use in certain ways. We use tools to do all sorts of things. One of the tools we can use is mathematics. We can take the world, we can apply that tool in the world. So think of that box as a tool that we apply. It's handily looks as though it could be a mobile phone. Now a mobile phone is a very ubiquitous tool that we use for many things. We can also use, including entertaining ourselves. Mathematics is also a mobile tool that we can use and carry around with us. We don't carry it around in our jeans pocket, we carry it around in our heads. But it can be used in the same way. You can just switch it on, use it, and then apply it in the world. So if you think of mathematics as the equivalent of a mobile phone carried around in our heads, that actually describes mathematics as it fits into society. Okay, let's look at one more example. This is a more topical one. 2 years ago, or 3 years ago now, the world faced a very new situation. We had this novel coronavirus coming out. Okay, it just came out of nowhere. You know, these things happen roughly every 100 years or more. And this thing came out. And the world, given its modern complexity in communications, had to respond extremely quickly. And so mathematics came on board within the first few days, because we have a well-developed mathematical-based tool, science, called epidemiology, which is both observational, it's experimental and laboratory, and it also has a strong mathematical component. It is a mathematical science. So there was in existence a whole mathematics of epidemiology. So that was the tool that people took to first, because what they wanted to do in the late part of 2019, the early part of 2020, was try to figure out in advance how bad this thing was likely to get. And so the first thing they did was take the epidemiology, take what little bit of data was known, a lot of it coming from China, where the thing sort of moved into the human population. And very quickly, various mathematicians, groups of mathematicians around the world were able to develop models. This particular model was developed at University College London, which has a very large and very powerful mathematical epidemiology group. And they found a mathematical model of what might happen. And they came up with a graph, and this was published actually on, I think, March the 16th, 2020. I remember the date because it was my birthday. And on my birthday, this thing came out, my birthday present as a mathematician at that stage, simply interested in what I could do to protect myself and my family, this graph came out. It wasn't a graph of what was happening. This was a graph predicting the future. This was what might happen throughout the first few months if this thing followed various paths. I'll look at that I'll blow that up in a minute to look at it. But what happened when that graph appeared was within days of seeing that graph, like 2 days or 3 days, all the Western societies locked down their societies. Not all of them. Most of them did. Sweden didn't. One or two others didn't. Some of them did it extremely detailed. China was a lead. Korea was a lead in total lockdowns. New Zealand locked down the country. Most nations locked down to some extent, at the very least by closing schools and universities, working from home as much as possible, and doing social distancing. And so they came up with various predictions of how bad things would get if they didn't do some of these things. And it was so dire in terms of the number of deaths that most countries did a lockdown and did various other things. If we look at that in a little bit more detail, these were the various graphs. This was looking to the future. It was interesting because many people were confused. I remember reading newspaper articles by leading American politicians saying, how can you possibly look at the future? This is a graph of the future. Well, they hadn't realized that people in mathematics and the various sciences had been drawing graphs to predict the future for a long time. It's just that was, for most people, a very novel idea. And so there were quite a few people who were skeptical that this worked, but scientists knew from using these things that they can be very reliable. They are graphs of what might happen, not will happen, but of what might happen. And it was enough to make decisions, because the red line along the bottom is the capacity of the various, this was for the UK, but it was a similar graph for all other societies. The red line, the straight line, is the bed capacity in the intensive care units. And then the various graphs are the number of sick people there will be that need attention, that needs to go into hospital on various societies. The top one was if nothing was done. And then you're up into 300,000. I mean, this was, you can read the scales. I mean, the actual numbers don't really matter in that sense. It's relative numbers. You're into large numbers of people very quickly, way beyond the capacity. So you would have societal disasters in many cases. So those were the decisions that were made on this very quickly. It's not perfect, but it's the best we've got. This is the most precision you can get about the future. And then what happened was, as the pandemic progressed, the graphs got more and more accurate because we had more data. You were moving forwards, and so these graphs were updated regularly on a daily basis. In fact, these things were updated, and those of us that spent time in mathematics actually used to look at these daily. We'd develop our own. I developed some of my own models just to see how my own simple ideas compare with the experts. And it was an interesting project to be a mathematician in, as well as been going through it. Okay, so that's another use of the mathematical cycle, and this is one that has affected our lives in a big way for the last 2 or 3 years and continues to do so. Sometimes when we use this, we have to develop new mathematics. In the case of the COVID, it was old mathematics, and pretty well all of the examples in that TV series were existing mathematics. You take some mathematics off the shelves, linear equations, differential equations, all sorts of parts of mathematics, and you apply them. That's typically how it's done. There's mathematics taken off the shelves. We've been developing mathematics for a couple of 1,000 years. There's plenty of stuff around. Actually, most of the mathematics that's been developed was developed in my lifetime, which is the last 75 years. So far more mathematics has been developed in my lifetime than before it. It's growing almost like an epidemic. So people who think that mathematics stopped with the ancient Greeks are a little bit out of date. Okay, but very often, or at least not very often, but quite often when we're looking at this cycle, we have to develop new mathematics. And in fact, using this cycle as a lens, gives us a way of looking at the history of mathematics, because all mathematics that's been developed has been developed for some reason to solve some problem that wasn't there beforehand. The first new mathematics that was developed, well, this is a little bit contentious, but there were two strands, and I'm going to mention them both. The one that's in many ways the first, and it's certainly the first in terms of drawing a direct line to present day mathematics, was the development of numbers. And numbers began, well, it depends what you mean by numbers, but people started counting at least 43,000 years ago by making marks on bones. We know it's about 43,000 years ago because we have physical evidence from anthropology, including this bone that's been carbon dated to about 40,000 BCE. So 43,000 years ago. Okay. There may be earlier ones. People before that, maybe people used to make marks on sticks of wood, but none have been found that have survived with the markings. So it's when you have bones that you get the oldest known survivals. And by trying to figure out what they were doing, anthropologists have come up with plausible explanations of what these things were. Oh, by the way, just going back to that, they think it was developed in order to follow cycles of the moon, to sort of follow the days, to try and think of seasons and so forth. It was believed to be keeping track of time in terms of the moon and that kind of thing. And so by looking at these, they've come up with hypotheses that these are ways of measuring time in a very crude way. That eventually, the idea of tallies, eventually, in a much more recent time, about 8,000 BCE, gave rise to symbols and arithmetic. And this happened in the region known as Sumeria, the Fertile Crescent in what's now known as the Middle East. And what happened there was the Sumerian society was so, it was one of the first advances. I'm giving the history of mathematics based in sort of Western Europe and how it came about. All of the similar stuff was taking place in China and Japan and the East. There was another whole parallel thing going on at the same time. The one I'm giving is the one that that led to the Western mathematical tradition, all of which have been fused now. So, but there were other histories. There was a South American history as well. This is the one that became the culturally dominant one just because of the various times and what was going on in the political world. There was a half a century when there was dominance by. There were several centuries when there was dominance in the Middle East and then Western Europe, and that sort of led to present-day mathematics. But it all eventually fused into one. But in this historical thread, what happened in Sumeria was society reached a level of complexity where people wanted to be more precise about trading goods. And in order to trade goods, you need to be able to count them and to keep records of them. And what the Sumerians did was they used to use little tokens to measure property. And so they would have tokens to measure bales of wheat, jars of olive oil, numbers of cows, sheep, and so forth. So they had tokens to measure things. And eventually they had to develop a way of keeping track of the tokens. First of all, your bank account consisted of your tokens for your objects enclosed in a piece of clay. They would take a clay sheet, they would take your tokens, put them on the clay, bowl it, turn it into a ball, seal it, let it dry, and then your bank account was the contents of that object. It was kept by a village elder. There was a banker, the village elder, kept everyone's parcels of things, and that was the bank record of your ownings. It got to be tedious to break those things apart in order to get at the tokens and literally compare them with, because they didn't have numbers, they were just tokens. You had to compare them with stand them alongside the objects. If you were trading sheep for goats, you would go through these tokens. So before they sealed up the tokens into this clay piece, they pressed the tokens on the outside. So there was a record on the outside of the tokens that were on the inside. Well, once you have a record on the outside of the tokens on the inside, you don't need all the tokens, you just need markings on the clay. So written symbols for mathematics were introduced as markings of objects that were inside the tokens. If you think about that for a minute, there's a modern day analogy of tokens that represent money that represents someone's worth. It's a credit card. So credit cards have actually been around for at least 8,000 years. Actually 10,000 years, because it was 8,000 BCE, where you had symbols and tokens that denoted your monetary values, your monetary worth, that denoted what stuff in the world you actually owned. All of this, by the way, was developed following groundbreaking work by what a then university, a graduate student at the University of Texas at Austin, Denise Schmant-Besserat, who was the one that went round Sumeria to the various sites, found all of these tokens, found all of these clay tablets, and after a lot of painstaking work was able to reconstruct the use of them and come up with the best theory we have. And it's a reconstruction theory of how numbers arose. And according to this reconstruction, numbers arose because they were money. Numbers are money, money is numbers. Money is simply one way of attaching numbers to the world. Physics gives you another way. You know, temperature attaches a number to the world. Mass attaches numbers to the world. Velocity attaches numbers to the world. Physics works by attaching numbers to the world. That is, in fact, the modern scientific method of physics. You attach numbers to the world. Commerce is the same. When you attach numbers to the world in terms of ownership of things, you get money. Okay. So that fits into this, because in that case, what the Sumerians did, and now we're using the mathematical cycle as a lens to look at history, and we're saying, what were they trying to do? They were trying to organize society. What aspect were they using? Trading. Trading that was done by tally systems, which were a way of keeping track of someone's possessions. They turned those tally systems into symbolic representations, initially on clay, then later on sand in the ground where you put markings, and then paper, and then modern credit cards, where you can't see the symbols with your eyes. You need to use technology to see the symbols. But the development of technologies is in the top right-hand corner, and it's all based on tally systems when it comes to commerce. And in this case, the new mathematics that was developed is arithmetic, adding numbers, multiplying them, and so forth, all of which correspond to things in the world, mathematical results. And then when you apply it to the world, what you've got is money. So that is a picture of the monetary cycle, of what money does in society. And since then, and this is just a classic, you see this in schools all around the world, something like this, at least in the Western world, because this is the history of the Western world, drawing on from various parts of the world as well, including the Hindu mathematicians in the first 3 or 4 centuries with Brahmagupta and so forth. This is the sort of the development of the modern Western tradition mathematics with its history. And if you go through that and you look at the major trends, it begins with the study of number. With the ancient Greeks, you get the study of shape becoming precise. With mathematics, you get geometry developing, laid on top of the number. You fast forward to the 17th century, you've got the study of number shape, you've got motion because calculus was invented. You've got the idea of the mathematics of space. Calculus was first of all developed in order to study continuous motion and to understand the motion of the planets. You've got probability coming along at the same time, the way to predict likelihoods into the future. And then go to the 19th century, you've got the use of that technology of mathematics. You've got the use of the mathematical cycle turned in on itself. Because what happened in the 19th century was mathematicians took the tools of mathematics, including calculus, which was initially developed to study continuous motion of the planets, and they used that framework to study mathematics itself. And that was the development of modern pure mathematics, which was occasioned by the fact that calculus worked, but was understood, people didn't understand it. Calculus was weird because it seemed to involve dealing with infinity, which is a weird concept. and calculus was developed to try and make, I mean, modern mathematical analysis. The theory of calculus was developed to put the practical use subject called calculus on a theoretical basis and to make people confident that it was a reliable tool. Okay. So from the modern perspective, what is mathematics today? The definition I like, it wasn't my definition, but this one came around roughly about the time when I was beginning to become interested in more than just pure mathematics itself, in the early 1980s. This phrase started appearing in the 1980s. I liked it so much that I wrote a book about it called Mathematics, the Science of Patterns. And I wrote that book deliberately to try and create this term, the science of patterns, as a meme. I say it wasn't my term, it was floating around. Various people were using it in talks and a few publications, but it wasn't established. And I was already interested. I used to write for the newspapers. I wrote for the newspapers in the UK. I was writing for newspapers and things in the United States. So I've always had a sort of a journalistic streak. And so I was very conscious of creating memes and ideas to popularize things. So I deliberately tried to make this phrase a meme by producing a book with that title. And that was part of establishing that. Another way of describing it would be the study of abstract structure, which is more meaningful to a mathematician, but doesn't have the same ring in terms of getting into TV. And that meme actually got it onto TV and so forth. At the same time that mathematicians were sort of exploring the idea of abstract patterns, so were the arts world. People in the arts world, including Picasso, for example, and one of my favorite, Kandinsky, were very much trying to use their artistic view of the world to look at the mathematical way of looking at the world. And if you look at these diagrams, yes, they are geometric structures, but they are clearly meant to represent things like worlds, universes, patterns you see in the world. This is clearly an attempt to show an abstraction layered on top of the real world. Cubism was another example of an art form trying to sort of look at the three-dimensional world with sort of geometric two-dimensional illustrations. The kinds of pattern that are used can be used to categorize mathematics. So counting, the patterns were involved with patterns of number, 3ness, 5ness, 7ness. That gives you numbers, it gets you arithmetic. When you start applying mathematics to those numbers themselves, you get a branch of pure mathematics called number theory. As an undergraduate, I fell in love with number theory. The only reason I didn't do a PhD in number theory was it would have taken more than 3 years, of which you can get funding in the United Kingdom in those days to do a PhD. It would clearly take more than 3 years to get to the frontiers of number theory. And all my advisors and undergraduate told me that. They said, if you want to do a PhD, you can't do it in number theory. You just won't have the funding to do it. Maybe get into that later, but do something else. Some people ignored that advice, people like Andrew Wiles, and they went and did it anyway much years later, and they ended up becoming great number theorists. But I believe them, or maybe they were being kind. Maybe my advisor said, you know, you're not the kind of guy who's likely to solve Fermat's last theorem, so pick something else. In any case, I did, but I still love number theory. It's a wonderful subject. There's the science of putting things together. This is modern algebra. Modern algebra is the science of putting things together. It looks at things like, what order do you put them together? Which things fit together? What happens when you put them together in a chain? Lego, it's the sort of the theory of Lego in many ways. It's a very abstract level. It looks at how things combine and put together in a discrete fashion. Patterns of shape are geometry. Patterns of measurements and things, when you combine that with geometry, you get things like trigonometry. Trigonometry is essentially geometry with measurement. When I earlier on said there were two histories of mathematics, one beginning with numbers, what I had at the back of my mind was there was another thread of trying to understand the space people live in. And that sort of gave rise to early geometry, early trigonometry, and that actually was a separate path from numbers and arithmetic. One was commercial, that was numbers and arithmetic. The other one was measuring the earth and navigating the earth, and that was essentially geometry and trigonometry. They all eventually fused together, but for many years they were separate. In fact, they were still separate in the 17th century. When Newton developed calculus, it was not calculus about numbers. It was the theory of space. His methods of calculus were actually applied to space, velocities and moving objects. It was only in the 19th century that was genuinely fused with numbers. So the idea that calculus is about numbers, that it connects with algebra and analysis and so forth, that was a 19th century development. Motion and change itself, one of my favorite artists again, Kandinsky, Marshall Duchamp, sorry, nude descending a staircase, one of my favorite paintings, because that's calculus. Calculus looks at continuous motion as a sequence of discrete motions. That was the idea of calculus. And Duchamp captured that beautifully. He looked at, his art looked at, just as Kandinsky looked at the sort of the geometric shapes of society, Duchamp looked at motion and how you can capture motion. Symmetry, why do we find flowers particularly attractive? Why do bees and birds find them attractive? Well, it's all to do with symmetry, and the mathematics we developed to look at symmetry is called group theory. And then more of this, more modern ones, patterns of position and closeness gives topology. So we can look at the different branches of mathematics by classifying the patterns on which they are based. They're different kinds of patterns. And the most recent one, patterns of real world data, gives a statistical theory. And there are many more. So now we can look at this diagram in terms of the emergence of new mathematics. So this is a lens on the history of mathematics. Think of how mathematical developments where new subjects come along, and this is how they all develop. You have a real world situation. That real world situation might be mathematics itself. It might be calculus used in the world. And in the 19th century, people said, calculus is being used, it's been effective, but we don't understand how it works. Let's look at the patterns of calculus and develop a theory of calculus and get new patterns. And new patterns came along. Once you've got the new patterns, you can describe, you can come up with a new mathematical description. You can then get, you've now got new mathematics. And you can do that mathematics and get new mathematical results and feed back either into the world or into mathematics itself. One example, the one I mentioned and didn't talk about, was geometry. Back in the day, well, even today, the Nile Valley floods frequently. And when it used to flood, the markings people put on that delineated the borders of their society, of their property, the markings would get obliterated. So they wanted a way to be able to reconstruct the land barrier, the land markings on people's properties. And that gave rise to what became eventually modern geometry. The phrase coming from the Greek geometron, meaning earth measurement, earth measuring. And it literally came out of attempts to form a way of recording the shape of the land, the space, and being able to sort of measure the boundaries and see where the boundaries are. The version of geometry that we see and are most familiar with is Euclidean geometry, because that was the version that was formalized by Euclid and the others in around 350 BCE. Okay, in terms of this, Euclidean geometry is just a mathematical model. It began as a model of the Nile Delta and other land masses where you want to keep track of the land. So it's a mathematical model. We began with that real world situation, and they developed a mathematical model of that real world situation. And that mathematical model was so useful in many other applications, it became itself a branch of mathematics. Another example, in the 9th century, the traders in the Muslim world that were trading along the Silk Route between Asia and between the Far East, between India and the countries that were producing the spices and so forth, and they were trading with Europe across the Mediterranean. And that trading was carried out by people on camels going along the Silk Route between Buja in North Africa and down in India and Ceylon and various places. And in order to be systematic about trading, they developed a new model of trading, which was written about in a book in the 19th century. And the title of that book in Arabic begins with the phrase al-jabra. And al-jabra became algebra. That book was written by al-Khwarizmi, whose name gave us the modern word algorithm, because al-Khwarizmi's book on algebra, which was a way of systematizing trading patterns, was so useful that people started using it all the time. So the methods of algebra described in the book called algebra yada yada, it's a long phrase beginning with the words algebra, which was one of the techniques in the book, gave us the modern subject called algebra. But it was a model. It was developed as a model for trading, to make trading more efficient. And it became a branch of mathematics, used many, many times in different ways. Modern algebra is slightly different, and that gives you the Lego shape thing. But sort of classical high school algebra is in the tradition of trading and commerce. Okay. Let me look, in fact, this is my last example now. I want to look at geometry itself as a mathematical model, because once you've got that picture, you can think of these models and see how they work. And why did geometry become a discipline in its own right? Well, because geometry is the mathematics of shape. And you can think of all sorts of things in the world in terms of shapes. There are many shapes in today's world more relevant than triangles. And in fact, the real power of mathematics itself, when do you need the actual mathematics rather than just a mathematical description? It's when you're trying to reveal invisible patterns. And many of the patterns in the world today cannot be seen, but they can be experienced. But you can visualize them using geometry. And you have to be careful about visualize, because visualize might have to go in quotes, because they might not be a visualization that you can see on a page or anything like that. So that's the idea. Patterns of shape give rise to geometric descriptions, and then you can do mathematics, and that means you're doing geometry, and you can use this cycle in the world with a new idea. And let me give this specific example: life in a multicultural urban society. Can you use geometry to understand the way people live in a modern, large city when they come from all over the world? Here's an example. This is Manhattan. It's a Chinatown in Manhattan. And someone who lives in Manhattan, there's an artist who's also a mathematician called Tony Robbins, a little bit older than me. He spent his career using mathematics to understand life in a modern city like Manhattan. Multicultural, multiracial, multigender, multi, all of those complexities coming together. And he said to himself, can I use geometry to understand that degree of complexity? And he was trained as an artist, but he went and studied with all sorts of mathematicians, including some very famous ones, George Francis, Tom Banchoff, and he learned about multidimensional geometry. And he started developing ways to see society, to see the shapes of living in a modern society using geometric ideas. Euclidean geometry clearly applies directly to the ancient world. That's the kind of shapes that were sort of around. This is an example, and these are artworks, but they're artworks designed to be ways of visualizing modern society. And this is based on mathematics. These are illustrations based on computer-generated images of mathematical objects. That's what he does. He generates various objects, then he plays with them until he gets one that looks aesthetically pleasing, and then he turns it into a piece of art. Here's one of them. And the idea is, this is a four-dimensional object depicted, or multi-dimensional objects taken down to 4 dimensions, that's then put into 3 dimensions, which is then turned into 2 dimensions. It's a bit like taking an object in the world, taking a photo on your iPhone, and the 3 dimensions of the world become 2 dimensions on the screen. Well, this is taking 4 dimensions or higher and projecting them down onto a screen. And so you can see the, and just as by looking at Google Maps with an aerial view, you can get a sense of travel. If you stare at these things long enough, it can give you some idea of how the different dimensions of life interact. How does gender interact with racial background, with language, with cultural preferences, with political views, with where you live, with what you're doing for a job? How do all of those dimensions of modern life interact? And what mathematics is underlying these artworks is mathematics. So it means there is a structure there. There is a mathematical structure that you can try and understand. That's a new kind of application of geometry. That's still Euclidean geometry, by the way. It is Euclidean geometry, but it's in 4 or more dimensions. And as I say, the computer can see 4 dimensions, 5 dimensions. It will see as many dimensions as you want, and you can get it to turn it into an illustration. So that gives your human eye at least some view of the complexity of the world in which people live in, when all of the aspects of our lives as humans are captured in geometry. So we can glimpse society that way. This is classified as art because art is the subject where you can see the world from the full complexity of the human mind. You don't have to simplify it as such. The idea is to get your mind into the right way. I and various other people have used these ideas to try to develop interfaces for intelligence analysis. In fact, the interfaces on my computer games from Brainquake are very simple examples of taking interfaces based on the ideas of how mathematicians solve puzzles. If you look at the puzzles my company develops, they are actually visualizations of how mathematicians think. At least they're visualizations of how I think. And that was the only person I had any insight to. But there are actually studies of how mathematicians think. And the way I think about mathematics is very similar to the way many other mathematicians do. And so those games are actually visualizations of how mathematicians solve problems turned into games, just like Robin's work is visualizations as pieces of art. And the idea is if you look at them and try to follow the connections, you'll get some sense of the complexity of modern life. And as I said, I certainly use that in interface design for tools for intelligence analysis, which is all about the same things. Intelligence analysts have to understand the world of modern life, all of its dimensions. You know, it's critical. If you don't take account of people's politics, their racial backgrounds, their languages, their geographics, then you can't do intelligence analysis. Modern intelligence analysis is looking at images like that. It has to be. Okay. As I say, that's still Euclidean geometry, but it provides us a way to help understand it. Of course, what the intelligence analysts do is they sit in front of a workstation so they can explore that. They literally explore it and try to come to an understanding based on their exploration of that. It makes the invisible visible. With our modern technologies, particularly digital technologies, we can see these hidden shapes. And finally, let me just mention that what's going on here is that we've got simple visualizations. Euclidean geometry is not the Nile Valley. It's a simplistic drawing of the Nile Valley. But most of the stuff about the Nile Valley isn't there. It's just a view of the shapes. Robin's artwork is a simplistic view of Manhattan. Very simplistic, but it's useful. And simplistic diagrams are the essence of mathematics. Let me leave you with the granddaddy of simplistic diagrams and the value we've had from society. The atom looks nothing remotely like that. That is not an atom. Every physicist knows that's not an atom. That is a simplistic diagram introduced in the 19th, early 20th centuries. But boy, has that been useful. The mathematics that's been developed on that model has given us most of the modern world. So don't be fooled by simplistic diagrams. the right simplistic diagram turned into the right mathematics is incredibly powerful. If you're interested in Robin, by the way, there's an article you can easily find by just Googling art critical Tony Robin, and it describes how he does his work and the mathematicians he consulted. That's that particular example. And I'm now going to leave you with this one picture, the granddaddy picture I wanted to sort of get across. This is the way to understand how mathematics is used in society. It's the way to understand how mathematics has been developed throughout history. This places mathematics in human life as a tool that we develop. That's where we do mathematics. That's how we use mathematics. And that's how we create new mathematics. That is mathematics in society. And I think it's a valuable way not only to think of mathematics when we're doing it, but also when we're inventing it. And in fact, most applications of mathematics today do not simply work in the model. They work with the whole picture. Except in pure mathematics departments of universities, mathematicians in society today work with the whole picture. The second half of my career has been working with the whole picture, which means I have to spend a lot of time talking with experts in different domains, because that's how it's done today. Only pure mathematicians have the luxury and the joy to work in isolation. That's important. We need new mathematics developed, and it's wonderful for anyone who can do it. I would recommend doing it, but it's now a small part of mathematics as part of society. Mathematics is actually a way of thinking, and that's the story. Okay, I'm going to kill that and then show myself off.
Thank you, Keith. Can you hear me?
Okay.